Let's talk about sum types. So the idea behind the sum type is, suppose that we have a value of sum type A1 plus A2. And this means that this value contains either a value of type A1 or a value of type A2, but not both, only one of them. So that's the idea behind the sum types. So therefore, there should be two different ways to create the value of a type, this sum type. From an expression E of type A1, we can somehow create an expression of a type A1 plus A2. And from an expression of a type A2, we can also create another expression of type A1 plus A2, because there are two different ways of creating a value of this sum type. So in the first case, suppose that we have an expression of type A1. From this expression E, we can create an expression of type A1 plus A2 using this syntax: injection left expression E. So this in left stands for injection left, because we are injecting to the left side. And in order to tell the type on the right side, we annotate this injection left keyword with the type A2. So expression E has a type A1, so injection left E has a type A1 plus A2, where A2 comes from here. So similarly, from expression E of type A2, we can create another expression of a type A1 plus A2 using injection right expression E. So this injection right, this is in right, which stands for injection right, because we are injecting to the right side. So expression E has a type A2, so we have something plus A2, and this A1 comes from this annotation. So expression E, the type of expression E goes to the right side, so it's injection right, in right, or injection right, and the type on the left side comes from here. So there are two different ways to create an expression of a type A1 plus A2, some type A1 plus A2, either from expression E of type A1 or from an expression of type A2. So now we can create expression of type is sum type. Now, how do we extract the value of value from an expression of type A1 plus A2? That is, suppose that we have an expression of type A1 plus A2. Now we'd like to extract either an expression or value of type A1 or another expression E of type A2. We know that this expression E has been created either with a value of type A1 or a value of type A2. But in general, we don't know which value has been used when we created this expression E. In general, it's unknown. So for instance, suppose that we have this lambda abstraction. In this lambda abstraction, this variable x has a type A1 plus A2. And because we don't have a concrete argument yet, inside the expression E, there's no way to tell which of type A1 and A2 has been used when we create the value for this variable x. So therefore, from an expression of this sum type, an expression E of this sum type A1 plus A2, in order to extract a value, either this one or this one, from this expression of a sum type, we have to provide two possibilities. The first possibility where a value of type A1 has been used, and the other possibility where a value of type A2 has been used. We have to provide for these two different possibilities, which means that in order to extract a value from this expression E, we have to perform case analysis. We have to perform case analysis. So with this syntax, we are performing case analysis on expression E. And if expression E has been created with this injection left, then it's going to have an expression of this form, injection left of x, where x is unknown yet. Let's say it is x1. In that case, we evaluate expression E1. Or expression E could have been produced with this injection right. So in that case, we assume that expression E is injection right x2. And in that case, we proceeded to evaluate expression E2. So this one means that suppose that expression E was produced from something like injection left value V with this A2. Then we are going to bind this variable x1 to the actual value V here, and then evaluate the expression E1. And similarly, let's just say expression E was produced with injection right with the value V. In that case, we take this second branch after binding variable x2 to this value V. So we take this branch. So this is the new form of expression for performing case analysis on an expression of this sum type. So this is the informal introduction to sum types. A value of sum type A1 plus A2 can be created either from an expression of type A1 or an expression of type A2, but not both. A value of type A1 plus A2 contains either a value of type A1 or a value of type A2, but not both. For that reason, given an expression E of this sum type, we have to perform case analysis to see which value has been used to create this expression E. Now let's formalize all these ideas into abstract syntax and typing rules and reduction rules. So syntax. So syntax for sum types is we use this notation A plus A, the sum type, and expressions now has this injection left expression E, and we annotated this injection keyword with another type A. And we also have injection right expression E. And similarly, we annotate this injection right with another type. And finally, we have this case expression for performing case analysis. Case expression E of if this is injection left some X, then we take this branch. Or if it could be injection right some variable X, and then we take this branch. So that's the extended abstract syntax that includes some types. What about the typing rules? So how do we decide the type of so how do we decide the type of this injection left expression E, where we have this annotation A2? If expression E has a type A1, then the whole expression is going to have this sum type, and it's injection left, so we place this A1 on the left side, and the type on the right side is obtained directly from this annotation, so it has A1 plus A2. And like the previous introduction and elimination rules, this rule is called sum type introduction rule left case, because if we read this rule top down, we end up introducing this sum type. So it's called the sum type introduction rule. Similarly, we have this dual case, injection right A1 expression E. If expression E has a type A2, then we are going to inject it to the right side. So we have this sum type here, and this A2 is injected to the right side, so A2. And the first component of this sum type is directly obtained from here, A1. So this rule is called sum type introduction rule, right case. Now let's talk about the typing rule for this case expression. So we'd like to find out the type of this case expression of, so this is expression E, and let's say this is injection left X1 and E1, or injection right X2 with expression E2. So what's the type of this case expression? So first of all, this expression E must have some type. It's going to have a sum type. Otherwise, the whole expression doesn't type check. Now, let's say we don't know, in general, we don't know which of type A1 and A2 has been used to create this expression E. So we have the first case where this type A1 has been used. So we analyze this branch. Now, we'd like to find out the type of expression E1. But in this case, expression E, we assume that expression E has been created with variable type A1, and the value is going to be stored in this variable X1. So in other words, let's say expression E was something like injection left value V, then this variable X1 is going to have this value V. So therefore, inside expression E1, we assume that variable X1 has a type A1. So we extend the typing context here with this new assumption X1 has a type A1. So of course, inside this expression E, we may use this variable x, and this variable x is going to be bound to the value that is used for creating this expression. So let's say this has type C, and similarly, we analyze the second branch. So we try to find out the type of expression E2, where we introduce a new assumption. X2 has a type A2. So X1 goes here, and X2 goes here. A2 goes here. Now, we have to actually we have to actually calculate the same type C from expression E2. From expression E1, we obtain type C, and from expression E2, we should obtain the same type C. Otherwise, this case analysis doesn't make sense, because we cannot tell in advance what is going to be the type of the final result, simply because in general, we don't know which branch will be taken at runtime. So therefore, we require that both types be the same here. So this is the C, this is the C. So therefore, we concluded that the whole case expression is type C. And the requirement here that both expression E1 and E2 have the same type can be compared to type checking this if then else expression that we looked at in the previous lecture. So of course, expression E must have type bool, and in order for the whole if then else expression to have some type C, we must show that expression E1 has a type C, and also expression E2 has a type C. Otherwise, we cannot assign a unique type C to the whole if then else expression, simply because at runtime, until we actually reduce this expression, so before runtime, we don't know which branch, this one and this one, will be taken at runtime. So therefore, both expression E1 and E2 must have the same type. For the same reason here, we require that these two expressions, E1 and E2, should have the same type C here. And this typing rule can be called some type elimination rule, because if you read this rule top down, you end up eliminating the sum type. So this rule is called the sum type elimination rule. So now let's talk about the reduction rules. This is the syntax for sum types, and these are the typing rules for sum types, which consist of 2 introduction rules and 1 elimination rule. Okay, now let's talk about the reduction rules. Similarly to the product types, we can think about eager strategy and lazy strategy, and let's just consider eager strat case only. In the case of eager strategy, when you have injection left some expression, you should actually provide a concrete value in order to count the whole expression as a value. In other words, this is a valid form of a value where we provide value here. So in the case of eager strategy, values include injection left value with some type annotation and injection right value with some type annotation. So that's the definition of extended definition of values under eager strategy. And what about the reduction rules? Suppose that we have injection left expression E. Under eager strategy, this is not counted as value. So perhaps there is a chance that this expression E reduced to E prime, in which case the whole injection expression reduced to this one. And similarly, for injection right, reduced to injection right E prime if E reduced to E prime. Now what about the case expression? First, case expression E of injection left x1 E1 or injection right x2 E2. So if E reduces to expression E prime, we reduce the whole expression to case expression E prime of injection left x1 E1 injection right x2 E2. Now suppose that everything goes okay and expression E eventually produces, for example, either injection left or injection right. So the first case is everything goes okay and this expression E produces something like injection left value V. So let's talk about this case. So now we have injection left value V with some type annotation. X1 E1 injection right, X2 E2. Now we can decide which branch can be taken because now we have a concrete value, injection left value V. So in this case, we are certainly taking the left branch. So we are going to take this left branch. So we proceeded to reduce the expression E1. And this variable x1, is going to be bound to the value given here. So we substitute value v for variable x1. And similarly, if this was instead injection right value v, then the whole case expression reduced to this time we take this right branch. So we take this expression E2 where this variable x2 is replaced with this value v. So we have two reduction rules here. So before we study the generalization of these sum types, let's see a simple application of this sum type. So previously, we introduced this product type, and as a special case of this generalized product type, we introduced the unit type. And now we have this sum type. And by exploiting this unit type and sum type, now we can encode Boolean type. Remember that the inherent capability of this Boolean type is to be able to choose one of two options. And now we have this sum type. Now we can express choosing one of two options. In this case, we can choose either left side or right side. So now we have two options. And so the idea is we encode this Boolean type with the sum type, either left side or right side. And what lies here doesn't really matter because we have already made our choice here. left side or right side. So to simplify the encoding, we just use this unit type here. So this is the way that we encode the Boolean type using unit type and sum type. Then true is encoded as the left side, which is injection left with unit. And the type annotation is going to be unit. And false is going to be the right choice, the right case, injection right. So we go to the right side, and this is going to be unit, and the type annotation is unit. Then what about if then else? If E, then E1, else E2. So we'd like to perform case analysis on the expression E, and if this is injection left, then we take expression E1. And if this is the right choice, that is, if it was created with injection right, something, then we take this else branch. And here, these two variables, let's say x1 and x2, these two variables will eventually bound to the unit value. So their computational contents are uninteresting, which means that inside the expression E1, there's no need to use this variable x, which is obvious here. There's no variable x. So we can think of these two variables, x1 and x2, as dummy variables that are never used inside these two expressions. So this is the way that you simulate this Boolean type by exploiting unit type and sum type. And finally, let's try to generalize. So just like we generalized product types, we can think about sum type A1 plus A2 plus blah, blah, dot, 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 an, where n is greater than or equal to 0. So this is generalized sum type. And the development of the typing rules and reduction rules is straightforward. And what is interesting is the special case of n being 0. N is set to 0, then what happens? So let's go back to the typing rules, syntax and typing rules. So in the case of n is set to 2, we have two forms of injections. Now, n is set to 0. So therefore, these guys are all gone. There is no injection. There's no way to create a value of some type when n is 0. Because simply speaking, these injection forms are all gone. Or from the typing rules, in the case of n is set to 2, we have two introduction rules. Injection, some type introduction left, and some type introduction right. Now what happens if we set n to 0? Then there are no introduction rules, which is consistent with our observation here. If n is set to 0, there's no injection expression. So these guys are all gone. Now let's talk about the case expression. In the case of n is set to 2, you have two branches. Now what happens if we set n to 0? Then we have no branches. So these guys are all gone. In the case of elimination rule here, some type elimination rule, the premise has two cases. Now, if we set n to 0, these two cases disappear because we get rid of these two branches. So we only have this case expression E. Then what is the uh, good name for this sum type when n is set to 0? There's no way, in the case of n is set to 2, there are two different ways to create a value of this sum type. If n is set to 0, there's no way to create a value of this sum type. So there's no way, so therefore we use this type void to indicate that there is no way to create a value of this type. So this is now void. And computationally, you should never be able to finish reducing an expression of type void because there's no value. So we replace this case keyword with abort. So in the case of n is set to 0, the sum type gives us an interesting type called void. And this abort expression, this is going to be now abort E. We don't have a counterpart of this abort expression in conventional programming languages, so it is only interesting in theory. But what that means is that what this expression, abort expression, does is, as indicated by the choice of this keyword abort, whenever you encounter this expression, you should abort the computation. If you insist and try to produce a value out of expression E, something bad could happen because there is no value for this type void.